So in this problem, we're going to basically design a synthesis for these molecules, starting from any material that has no more than 6 carbons. Okay, so let's take a look at the first one. Obviously, there's more than 6 carbons out here. So the key to think about this is like, how can we break this down? Okay, so what I'm going to do is, this is going to take a lot of room. I'm going to put this molecule on a separate page. Okay, and we're going to strategize about it on this page. Okay, all right, so the molecule is this. So first we're going to do the retrosynthesis. Okay, so we're going to think backwards, and then we're going to do the synthesis, and we're going to take some shortcuts out here for the retrosynthesis. So let's think about, basically, if I want to start with 6 carbons or less, then that means my starting material, one of the rings could be a benzene ring, right? And then I can think about, how do we add all of this? Okay, so if I think backwards from here, one of these, so we'll just put that, make this ring the benzene ring. So there's the 3 bonds, the double bonds, could be the benzene ring. And then now we have to think backwards, how do we kind of get this group out there? So we know, since this is an ether, we could make an ether out of an alcohol. So I think backwards from there. So that could be an alcohol. And then could we potentially change that alcohol? Could we potentially make that alcohol from an alkene? Yes, we could. So we put a double bond out there. And now, could we make this alkene by a dehydrohalogenation? Yes, we could. So we'll put a bromine out here. Okay. And then if I kind of take this backwards a few more steps, okay. Well, what if I know how to add a bromine out here? So if I take that one step back, then I get this. And then how do I add this ring out here? I could do it a few different ways, but we can use a Friedel-Crafts acylation. So that could have come from a Friedel-Crafts acylation, which means that it would have to be a double acylation. So something like this. These two would have to be added. And then that could be from this starting material and this kind of a acid chloride. Okay. All right. So now that we understand this route, we're going to go ahead and begin to synthesize it. So this was my retro synthesis. Let's take a look at the synthesis. So I just have to the synthesis is going to do the exact opposite of the retro. Okay. So we'll start with the benzene. I'm going to rewrite this compound a little differently, just to accommodate it on the arrow, over the arrow a little better. And that gives me a double Friedel-Crafts acylation, giving me this product. Okay. Then what I'm going to do is I'm going to get rid of both of these using, I could do the Clemmensen out here, Clemmensen reduction, zinc HgHCl, and that would give me this. Then I'm going to go ahead and brominate this position. So NBS is a good reagent to use. And I'll just go ahead and write the product out here. There we go. And then if I add KOH and ethanol, it's going to basically do an E2 elimination. So it's going to grab the hydrogen that's sitting out here and going to pump off that bromine. There you go. And now I want to add an OH at this position. So for that, I'm going to take BH3. So I'm going to do a hydroboration essentially. BH3THF, follow that up with H2O2 and OH minus. And that gives me the OH out there. Now I want to think Williamson's ether synthesis. So I take sodium hydride, which is a strong base, step 1, and follow that up with methyl iodide. And that's going to give me the product. And there you have it. But now, sorry, you don't have it yet because you're really trying to make the molecule with no benzene out there, right? So you really have to take this one step further. So if I take that one step further, that's going to be, I can take rhodium, carbon, okay, and you hydrogenate it, okay, and that's going to be, that's going to get rid of the benzene, the aromaticity in the benzene ring, giving us this as the product. All right, so the next compound on this list, so that was the A. If I look at B out here, B looks very similar to A, except for there's that little bond missing. So maybe we can take the synthesis of A a little further to figure out how to remove that bond. So what we can do is, for B, for B, I don't know why that got erased. We can think about, could I add something out here at this position? So what I could do is I could just take this one step further and do Br2H nu, and that would put a bromine at the most substituted position, that is out here. And then if I do a KOH ethanol again, that would create a double bond right in between the rings. And then I could just cleave that double bond using an ozonolysis. So that would be ozone. Step 1, you can use CH2Cl2. Step 2, you could use zinc and acetic acid. And basically, you'd end up with a double bond out here. Double bond O out there. Okay, I just made this look a little weird just to kind of make sure that the ketone groups are not clashing. Okay, and then I want to get rid of the both C double bond O's. At this point in time, I could use the Clemmensen or I could use the Wolff-Kishner. Sometimes I like to use different reagents for the same conversion, just so that it kind of helps my memory. So you could do the same thing. So the Wolff-Kishner is what I'll choose to use out here. KOH, NH2, NH2. And that would give you this. Oops.